So, hello everyone again. This is lecture 3 part 1 of wave optics. In the last lecture we were talking about the refraction and the reflection properties based on wave propagation of light. Today we will move on with a further discussion. So, I am Sameer Lavankar. Let us get started again. So, the course outline for you, first of all, so we started in the first lecture with the introduction concept. So, in this first of all we started with the corpuscular model of light, in which Descartes told us about how the model of light was being used or being propagated as tiny models. Corpuscles is nothing but very tiny particles. So, in that model it was occurred that everything which lies propagates in a straight line, or in the every property of light based on reflection or refraction was based on corpuscular model of light. But then after the further analysis was being done by scientists such as Young's, such as Huygens, etc., wave model of light was propagated, wave model of light was introduced, and hence the distributed the differences between the corpuscular model and wave optics is being considered, and this was all based on the first point, that is introduction of the wave optics chapter. Second, in which we studied about the Huygens principle. In Huygens principle we studied about the wavefront concept. First of all, what is wavefront, how it is created and all. Then we also studied about, if we know the wavefront at some time t is equal to 0 and we need to find it at some t is equal to tau, then using the concepts of geometrical construction and all, we can make a second wavefront. Either it can be a plane wavefront or it can be a spherical wavefront. So, this was being talked about in the second point here. And the third point was refraction and reflection of plane waves using Huygens principle. This is the concept we are talking right now. So, this concept is based on how the reflection and the refraction properties are being studied. How first of all, in the last chapter behind this, that is ray optics chapter, we considered how the discrete particle theory is being utilized to understand the laws of reflection and refraction. So, in this refraction properties we used an incident wavefront and a refracted wavefront, either from a denser medium or from a rarer medium. Then using the same principles we also find out proved the law of incidence is equal, angle of incidence is equal to angle of reflection, hence the reflection laws are also being proved. And finally, we were talking about how the behavior patterns change, or how the behavior patterns of prisms, lenses, etc., can be proved using the wave theory. So, in the last lecture we understood for the prism or a thin prism. Today we will move on to the discussion of convex lenses, concave mirrors, concave lenses, etc. So, let us move on with this discussion, and after completion of third point we will go with a new concept. I will tell you in detail what is coherent and incoherent addition of waves. So, let us move on with our discussion. So, this will be dealt in further classes. So, just a little brief about refraction and reflection of plane waves using Huygens principle. So, in the last lecture we first of all started with the refraction of plane waves. In this, this was a incident wavefront, and after the refraction, for this point it is V1 tau, but on incident at this point, if you want to make a wavefront for time t is equal to tau, then the radius will be equal to V, which is equal to V1 into tau, which will be the radius. Hence, the spherical wavefront is constructed, and hence when we draw a tangent from E point to the C point, this will be a refracted wavefront. So, this is how we get a refracted wavefront. Moving on to the next point now. So, this was the complete concept for refraction of a plane wave. Then next was we got a new equation which was related to the refraction, which was based on, which is also known as Snell's law. For deriving the Snell's law, first of all we assumed we defined one of the more concept, that is known as refractive indices. So, refractive indices is nothing but denoted as N1 is equal to C by V1 and N2 is equal to C by V2. So, these were the refractive indices for the medium 1 and medium 2 respectively. So, moving on, what was the first Snell's law of refraction? Snell's law of reflection was nothing but, if we know the angle of incidence, if we know the angle of refraction, if we know the refractive indices of the medium 1 and medium 2, medium 1 and medium 2 are nothing but the interfaces above and below mediums. So, the Snell's law of refraction states that N1 into sin I. What is the I? I is the angle that the ray makes at the interface in the first medium only. So, it will be angle N1 sin I is equal to N2 sin R. What is N1 N2? N1 and N2 is nothing but the refractive indices. So, this is the equation which we got in the last lecture only, that is N1 sin I is equal to N2 sin R. Quite easy to remember, these are both for the first medium and these are both are for the second medium. So, moving on, then we considered the concept of wavelength. So, let us suppose that this value is equal to lambda 1, then using the Huygens principle and all the previous data for wave theory which we had, we found that the medium 2, this V2 tau is nothing but lambda 2. Then using some mathematical formulation, what we got was that the ratio of V1 by lambda is always constant. Hence, even with the change in medium, the velocity is changing, but the frequency, that is equal to V by lambda, is always constant, that is it remains the same. So, this was a complete discussion that was told in the last lecture only. Then moving on with the refraction at the rarer medium, similar thing. First it was at the denser medium, now it will be at the reflection at the rarer medium. Only the length of V2 tau is now greater than V1, because this time V2 is greater than V1. Hence, the refraction is like this. In the last discussion, it was a little less than BC value. So, this is again the same thing, but this time also the value of the refraction formula, that is Snell's law formula, that is N1 sin I is equal to N2 sin R, is always persistent in each of the concept, either denser medium or the rarer medium. Moving on, then we also considered the, so after the refraction laws are being proved, then we also tried to prove the reflection laws, and then this concept was being analyzed in the last lecture. So, without wasting any further time, let us move on to the today's concept now. So, today we will try to understand the behavior of how the light propagates using wave theory according to the patterns which are visible in either prisms, convex lenses, concave lenses, convex mirrors and concave mirrors. How is the diverging occurring, how is the converging occurring, and so on. So, please look over here carefully now. So, let me start again. So, in the last lecture I also explained to you the behavior of prism, I will explain it to you again. So, now please look over here. So, once we have the laws of reflection and refraction, the behavior of prisms, lenses and mirrors can be understood. So, here we describe the behavior of the wave fronts as they undergo reflection or refraction. So, this was being understood in the last lecture only. So, in the figure A, so this is the figure being talked about here, we consider a plane wave. So, this is a plane wave, anything which is passing through a single plane. So, this is a sheet, this is a complete sheet. In this sheet, if we try to find out the value of anything which is passing through this perpendicularly, let the area vector is like this. If the area vector and the direction of propagation of the wave is similar, then it is known as a plane wave. So, this is an example of this is a quite a easy example of a plane wave here. So, the incident plane wave is coming across a triangular prism, a thin prism. So, in the figure A, we consider a plane wave passing through a thin prism. Clearly, since the speed of light wave is less in glass, quite evident, as you also understood in the last two lectures, that V2 is less than V1 if the incident is in air and the passing or the refraction is in water. So, clearly, since the light of speed waves is less in glass, the lower portion of the incoming wavefront, which travels with the greatest thickness, quite evident that the thickness will be higher here and thickness will be lower here, will get delayed. So, quite evident it will get delayed, hence the value will be if the propagation can be shown by my hand. So, let this be the wave front. So, it comes, then it keeps on tilting, and finally, when it reaches here, it goes in this direction. So, this is the complete let us say time lapse of the complete wavefront happening. So, it will come, then it will keep on start tilting. Why it will go keep on tilting? Because this portion, the below portion is getting delayed, and after the complete thin prism is being passed upon, then the wavefront will go down. So, this is the complete thing being talked about in this point. So, just to iterate to you what is written here again. So, in the figure A, we consider a plane wave passing through a thin prism. Clearly, since the speed of light waves is less in glass, the lower portion of the incoming wavefront, which travels with the greatest thickness of glass, will get delayed. So, this delaying is happening here, resulting in a tilt. So, this is a tilt, quite evident tilt. Tilt is here from the vertical direction, resulting in a tilt in the emerging wavefront as shown in the figure. So, this point is also completed. Now, please look over to this point. So, here what is, there is again a incident plane wave, but what happens after it passes through the mirror or lenses will be understood here, the behavior will be understood here. So, in the figure B, we consider a plane wave incident on a thin convex lens. So, this is nothing but a thin convex lens, and this is nothing but a what we can say, this is, let me explain you this afterwards. So, now, so on a thin convex lens, the central part of the incident plane wave traverses the thickest portion, quite evident this is the thickest portion here, and as we go above or below, the thickness is decreased. Hence, the maximum delay which will happen will be in the central portion, and the minimum delay will be happening in the top and below portion. So, quite evident. So, as you can see, the delaying has been happening maximum here, and it keeps on decreasing in the above part also and below part also. Hence, the wavefront which we will get is this is the wavefront being talked in the dashed line. So, this is the wavefront after it has passed through the thin convex lens. So, that is only written here. So, the central part of the incident wave traverses the thickest portion of the lens and is delayed the most. The emerging wavefront as in the wavefront which gets passed through the convex lens. The emerging wavefront has a depression at the center, quite evident. So, this is a depression here, anything which is depressed. So, and if I have a piece of paper, if I have a piece of paper and if I press it here, so if the molding is being happening like this, if there is a pressure or there has been a groove here, so this is nothing but known as a depression. So, the emerging wavefront has a depression at the center and therefore, the wavefront becomes spherical. So, quite evident, you can see that it has taken a form of a sphere and hence it is known as spherical wavefront and converges to the point F. So, as you can see, all the wavefront's direction is now towards a particular center point, which is also known as point F. So, this is that point F being talked about here. Moving on, so thickest portion is being done. The emerging wavefront has a depression at the center and therefore, the wavefront becomes spherical and converges to the point F, which is known as the focus. So, this is the only focus which you also understand in the concepts of ray optics. When the concepts of convex lenses, concave lenses is being talked about in the last lecture, then also you understood the concept of image, focus and all. So, this is nothing but the same focus which we talked in the ray optics chapter also. So, let us move on. So, this was the analysis, this was the behavior pattern of thin convex lenses. Moving on to the next point. So, now in figure C, so this is the figure C we are talking about. So, in the figure C, a plane wave is incident on a concave mirror. So, this is nothing but a concave mirror. So, this is nothing but a concave mirror for you. So, a plane wave is incident on a concave mirror and on reflection we have a spherical, quite evident, mirror is a reflecting surface, so there will be no refraction or very minute refraction, but for your studies, for your 12th class analysis, it is quite evident, it is quite clear to understand that a reflective surface is complete 100% reflective, hence complete reflection will occur and no refraction would occur. Therefore, anything which is passing or putting incident on a mirror will always get reflected. So, a plane wave is incident on a concave mirror. So, a concave mirror is in the figure C, and on reflection we have a spherical wave converging to the focal point F. So, here also when the wavefront was being formed, again a spherical wavefront was being formed. Again a spherical wavefront was being formed, which was again converging at a point, and that point is defined as focus, denoted by a letter capital F. So, this is the behavior pattern of concave mirror. In the similar manner, we can understand refraction and reflection by concave lenses and convex lenses. So, similarly, as you can directly see, for example, if I tell you about a lens, so quite evident that the maximum portion is getting delayed. So, this incident wavefront will get delayed from this portion and the minimum delaying will be happen from this portion. Just to iterate to you by writing. So, delay is maximum and this point delay is minimum. This point delay is minimum. So, similarly, we can also understand the concept of concave lenses and convex mirrors. So, let us go on with the further discussion now. So, in a similar manner, we can understand refraction and reflection by concave lenses and convex mirrors. From the above discussion, it follows that the total time taken from a point on the object to the corresponding point on the image is the same measured along any ray. So, now please look over here carefully, what does this point try to explain to you. So, let us take this B case only. Let us take this B case only. So, what is happening is any point which is happening as a wavefront. So, what we are explaining is for a ray optics concept, what we did was anything which is is being incident on any surface, it is a complete ray only. But when we try to explain the concepts, for wavefront, it is explained in the form of a complete line. So, let us understand that this is the line which is being incident on a surface. So, after the wavefront is being formed, after the complete, let us say a convex lens or concave lens is being formed, that ray of line is being closed apart. So, this is the complete what we can say spherical wavefront being formed. So, any point or any image which is being processed by this line is getting converging at the same point. So, as we already understood when we were trying to understand the concept of wavefront being formed at some time t is equal to tau, as every point, what is a wavefront? Wavefront is nothing but the locus of points which are being at the same distance from the source. That means, if a wavefront is being formed, when it will try to converge or diverge at any point, the time required will be same. Also, if the medium is not being changed for any part of that locus, then the velocity will also be same. So, if the velocity and time being same, time is always independent, so it does not depend. If the multiplication of velocity and time, that is equal to radius, is always same, that means the time required for each of these points or each of these locus of points to understand or to converge to that point f will be same. Hence, that is the only point written here. So, it does not depend that the light is coming from the top portion or from the middle portion of the lenses. The time required to converge it or the time required to form that image will be same. It will not occur like this, that the top portion of that image will be visible to us first and the middle portion will be visible after. Whenever you are seeing any image, the complete image is being formed at the time when it is happening, either from the top portion or from the middle portion. So, that what does this line try to understand, I will explain to you pictorially also. So, what is happening is, let us say this is the incident plane wave, and after the propagation of the plane wave front from the, let us say, convex lens here, what is happening is, this is the spherical wave front. So, now each point on this spherical wave front is at equidistant from this point f. What is this point f? This is the point f at which the image will be formed. So, at this point when image will be formed, because the amount of time required and the velocity is same, hence the amount of image carried by each of these points, either top or above, top or below, will be same. Hence, this line is proved. What is proved? That the image will be formed at the instant when the image is being carried from the left point to the right point. So, this point is also completed. Now, for example, when a convex lens focuses light to form a, so the explanation which I told you by mouth is written here. So, for example, when a convex lens focuses light to form a real image, although the ray going through the center traverses a shorter path, quite evident it will traverse a shorter path and these will take a longer duration. So, this distance is quite larger as compared to this distance. So, if I tell you by two different colors, let us say this is the distance first and this is the distance which is second. So, let us say I denote this by distance 1, distance 2, let us write it as d2 is greater than d1, quite evident. So, d2 will be greater than d1. So, although the ray going through the center traverses a shorter path, but because of the slower speed in glass, the time taken is the same, because the time taken by distance d1 will be maximum in the central portion, because the velocity gets delayed in the different type of lenses, different type of glasses being formed, absorb a time which the second distance is being taking is little higher, because the speed is getting delayed for a shorter duration of time. Hence, the image will be formed at the same time. So, the time taken is the same for rays travelling near the edge of the lens. So, this was the only explanation which I also tried to explain to you. So, this is a complete concept of behavior of patterns of what we can say the thin prism, then convex lenses, concave mirrors, convex lenses, convex mirrors. So, let us move on with the further discussion. So, now there is an interesting concept known as the Doppler effect. So, what is the Doppler effect? I will try to explain to you with figure also. For now, just focus here. First of all, I will read it and then I will explain to you what is happening and what is the actual change, what is the reason for this Doppler effect to occur. So, please look over here carefully now. So, what is Doppler effect? So, one should be careful in constructing the wavefronts if the source is moving. So, till now anything which we were trying to understand the concept using wave theory of light, we understood by the source being stationary. Let this be the source we are talking about, source being stationary. Source is stationary at this point. So, what is happening is, let us say I tell you the example, same example of let us say a stone is being thrown at a calm pool of water. So, what will be happening is, you can find the circular ripples being formed. So, then these circular ripples, if I try to use it, I try to view it from the upper bird eye view position, you will find the wavefronts being formed like this. Just let me change the center portion for more clarity. So, this will be the wavefronts being formed. So, if these are the wavefronts being formed, these are the wavefronts formed when the stationary position is happening. The source is always stationary, but this wavefronts are different. These formation of wavefronts are different if the source is not moving. So, this change in frequency which is happening due to the change in the movement of source is nothing but a phenomena called as Doppler effect. So, how are these figures being formed? What is happening if the source is moved right or the source is moved left? We will try to understand it. For now, I just wanted to explain to you a little bit about what is Doppler effect, how it is happening. In the next lecture we will start with Doppler effect only. I will try to make you more clear with the figures and all. For now let me end this lecture here only. So, in this lecture what we studied was, we studied the behavior of prisms, we studied the behavior of convex lenses, convex mirrors, concave lenses, concave mirrors, and also that the time taken to form the image will be same, because for even if the distances from the central portion or the above edges portion are different, because the time taken by the glass is that because the velocity gets delayed in the glass in the center portion, the time taken by the image to be formed is same. So, this was a final proof, and then I told you a little bit about Doppler effect. For now let us end the discussion here only. In the next part I will explain to you by starting our discussion on Doppler effect. So, for now thank you.